So now let's go the opposite way. Let's calculate molar solubility from KSP. Here's another example problem. We're given the KSP of barium sulfate being 1.1 times 10 to the negative 10th, and we're asked, what is the molar solubility of that barium sulfate? Again, I always start off with the equilibrium expression. So I'm going to write down solid barium sulfate dissociating into soluble barium and sulfate ions, and write down the KSP expression. And that's going to equal 1.1 times 10 to the negative 10th. Well, if I define my molar solubility, the maximum number of moles that will have dissolved in water for barium sulfate as X, then according to stoichiometry, the number of moles of barium with a 1-to-1 molar ratio can also then be defined as X. Same thing with the sulfate, 1-to-1 molar ratio. So if I want to know the molarity of those components, I can simply plug them into my KSP expression and solve. And in this case, X will actually equal the molar solubility, and that's going to come out to be 1.0 times 10 to the negative 5th molar. And that's our final answer. But what about something slightly more complex, like, let's say magnesium hydroxide? We know that the KSP of something like magnesium hydroxide is 1.5 times 10 to the negative 11th. And I would like to know the molar solubility of saturated magnesium hydroxide in solution. So again, let's start off with the equilibrium expression. And notice here now we have a 1-to-2 molar ratio happening. We can go ahead and write out the KSP expression. This time it's going to equal the concentration of magnesium times the concentration of hydroxide squared. And again, that still equals 1.5 times 10 to the negative 11th. So now let's backtrack in our problem. If I wanted to find the maximum number of moles of the magnesium hydroxide, the maximum molarity of magnesium hydroxide that could have dissolved, let's define that as X. Then according to stoichiometry, the moles of magnesium hydroxide as compared to the moles of magnesium is going to be the same, so that can be defined also as X. But 1-to-2 molar ratio, my concentration of hydroxide ion here has to be defined as 2X. So now I go to plug those numbers into my equation, and I'm going to find X times the quantity 2X squared equals 1.5 times 10 to the negative 11th. When you go through and you do all your lovely little algebra here, X comes out to be something wholly different. And I find it to be 1.6 times 10 to the negative 4th. Now, although we can't directly compare the solubility of barium sulfate with magnesium hydroxide just by comparing KSP values, because they don't dissociate into the same number of ions, I can compare their relative solubility by looking at the molar solubilities. So here we can see the barium sulfate, even though it had a much larger, by a factor of 10, KSP value, its molar solubility comes out to be 1 times 10 to the negative 5th, whereas the magnesium hydroxide comes out to be 1.6 times 10 to the negative 4th, much more soluble than the barium sulfate. So if you really want to compare which chemicals are more soluble in water, make sure that you're always comparing that molar solubility, never the KSP. As long as they have the same number of ions, then yes, you can use the KSP to compare.